All right, so still a couple of odds and ends that we need to pick up on using solubility, and we're gonna hit our last equilibrium topic. Is going to be dealing with how things dissolve, and a lot of times solubility or how things dissolve is governed by equilibrium. Even though we haven't treated it that way to this point in Chemistry 110, in Chemistry 111, that's the way that it actually works. And so we're going to move from acid-base chemistry onto solubility. And this might be a great time to talk about the idea of, I haven't really mentioned the textbook at all. I make the assumption that probably some of you haven't gotten your stuff out of your rooms here from your residence halls. You may not have your textbook along with you. And so I'm sort of working through the semester as if you don't have that available to you. So I don't necessarily expect you to be doing problems or anything from it or necessarily reading the chapters. I understand that we're sort of in crunch time and I've got to communicate the material as best I can within the lecture setting. So I just wanted to talk about that while we're at. The reason why I say that is because solubility would have bumped us into the next chapter, which was other applications of equilibrium. So in order to really understand this and really understand solubility, we want to talk about the idea of electrolytes. I fully expect that you understand what an electrolyte is. Electrolyte is something that whenever you dissolve it in solution, it will produce some ions. We know there are some consequences to that because ions in solution conduct electricity. And so things that dissolve and dissociate completely in solution to produce ions, we call those strong electrolytes. Sodium chloride, when you put it in water, breaks up completely into a sodium ion and a chloride ion, a cation and an anion. All right, and when you place that in an electric field, you'll find that those ions will move around to conduct the electricity through the water. In theory, if you took water and you stripped all the ions out of it, we call that distilled or highly deionized water. Technically, it shouldn't conduct electricity. So, if you really want to have toast in the bathtub, you probably want to do it when you're having a bath using distilled water. Don't really try that because soggy toast really sucks, but in theory, that's what you could do because pure water doesn't conduct electricity very well at all. It takes ions dissolved in it to really make it a strong conductor. And strong electrolytes do that. Weak electrolytes are compounds that only dissolve or dissociate partly in solution. So acetic acid is a good example of that. We talked about vinegar and how we looked, and through all of our calculations, we saw that vinegar may be 1 or 2 or 3% dissociated or ionized in solution. Mainly it doesn't ionize at all. And so it gives you the idea that, weak acids are really kind of weak, but they also then are really weak electrolytes because they don't produce tons of ions to conduct the electricity. And so you probably saw that in Chemistry 110 by looking at the light bulb. You can get this light bulb thing and it has 2 electrodes on it and you place it in the solution, and if it conducts, the light bulb glows like really bright, and if it doesn't conduct, then it doesn't glow very brightly. You probably saw that type of an experiment done, and if not, you can look for it either on YouTube or on the internet, and you'll be able to find something like that. I figured since it's a 110 material thing, I'm not going to talk about it here. But when we talk about the idea of strong electrolytes, there are a couple things that we've talked about already that are strong electrolytes, and those are acids and bases, strong acids and bases. We know that strong acids dissociate or break up or ionize completely, and strong bases dissolve completely in solution. And so those are very strong electrolyte solutions. But something that we had, the other thing that we haven't really talked about explicitly, but we thought about, is the idea of a highly soluble ionic salt. So sodium chloride, if we drop sodium chloride and we talk about how it dissolves to produce the cation and the anion, the sodium positively charged ion and the chloride negatively charged ion, and that conducts the electricity. When it does that, and it's a strong electrolyte because it's so incredibly soluble, all right? It's a highly soluble ionic salt, ionic compound. And so, whenever you have these highly soluble salts, there will be a limit at which it won't dissolve anymore. It's like this stoichiometric thing. You can readily determine how much of it's dissolved very readily. And this should be a little bit familiar whenever we think about the strong acid and the strong base, where if we calculate the pH of a strong acid solution, we just need to know the molarity of the strong acid in order to get there, or the strong base, to get the concentration of H plus or OH minus. So if we have something like sodium chloride and we put it in solution, 1 mole of sodium chloride produces 1 mole of sodium ion, or 1 mole of sodium chloride produces 1 mole of chloride ion when it's dissolved in solution or dissolved in water. So it's stoichiometric in the same way that strong acids and strong bases are stoichiometric. So if you take 2 moles of sodium chloride and dissolve it in solution, you'll end up with 2 moles of sodium ions, 2 moles of chloride ions. It's directly stoichiometric. We use that ratio in the balanced chemical equation. And when we talk about this, it is a single arrow, right? So talking about the solubility of something that's highly soluble is really the first step to us talking about solubility. So if we take sodium chloride and we start dumping it down in the solution, it's going to dissolve almost immediately to produce sodium ions and chloride ions that we've talked about. Now, the thing about it is this is highly soluble, so a lot of it is going to dissolve. Like you're going to start pouring that sodium chloride and a lot of sodium chloride is going to dissolve. And let's imagine that we've got this beaker and we've got 1 liter of water in it. That sodium chloride, the amount that's going to dissolve in that 1 liter is going to be about 360 grams, which is a massive amount. It is highly, highly soluble. Once we get to the point where we've added 361 grams to that liter though, it's not going to dissolve anymore. It's going to stop. Because at that point, when we get to 360 grams dissolved in that 1 liter of water, it becomes what we call a saturated solution. We have dissolved as much of that salt in there as we possibly can. We've saturated the solution. When we talk about highly soluble salts like sodium chloride, the way that we express their solubility is just like this. We figure out or determine how many grams of that compound will dissolve in a liter of whatever solvent we're talking about, in this case water. And that's how we report it, because it's very, very soluble, all right? It's stoichiometric, it dissolves. We don't have to worry about any complicated equilibrium to describe this process. We just know 360 grams will dissolve in a liter. All right, it's straightforward, it's simple, in the same way that strong acids, strong bases were straightforward and simple. When I say simple, I don't mean easy, I don't mean trivial. I mean simple as in the way that we deal with it is relatively straightforward. Now, we can talk about not just strong electrolytes, we can talk about weak electrolytes. And 2 of the type of weak electrolytes we've seen already, weak acids and weak bases. You put the weak acid in solution, it doesn't completely ionize, it only partially ionizes, all right? You put the weak base in solution, it only partly takes protons from whatever acid might be around. And that's generally less than 5% that occurs, so they're pretty weak. And that means that they generally are very weak electrolytes. We would have to have very high concentrations of the weak acid or the weak base for it to be a strong electrolyte. But also, we can have certain ionic compounds, ionic salts, that don't dissolve very well. And you might say, oh yeah, if I would throw iron oxide into water, it would probably dissolve just like sodium chloride, and you would be wrong about that. It doesn't dissolve in the same way. It doesn't dissolve in nearly the magnitude. And when I say nearly, I mean not even close. And we're going to see that here coming up in a second. Now, when we're dealing with slightly soluble salts, it's not stoichiometric in the same way that highly soluble salts are stoichiometric. Right? With slightly soluble ionic compounds, we actually have to use equilibrium to figure out. And you might say, okay, well, it's equilibrium. It's going to feel very similar. It's just that, remember whenever we said acid, we said there's a certain chemical equation that we have, a certain chemical formula that we use, equation that we use to describe the equilibrium of an acid. And then we said when we have a weak base, you have to have a reactive weak base with water, all right, to get the conjugate acid and hydroxide ion. Solubility is going to be the same way. It's going to be that we have a very specific form of the chemical equation that we deal with, and once we get there, it's just straight equilibrium. You've done it before, all right? And so, we have to handle this equilibrium because these things dissolve, but they dissolve according to equilibrium. And it turns out that almost anything that you put into water, even things that we've talked before about being non-soluble or not soluble, those things are soluble as well, at least to a very small degree. So to take an example, so here in 1944 is this statue of George Washington in New York City, okay? And you can see it looks very, very nice. It's made of stone, okay? It's made of limestone. So, you'd think stone doesn't dissolve, right? If you put a stone into water, it doesn't dissolve at all. I mean, you can't see that it changes mass or anything. But here it is, and this was, 2006-ish, probably even a little bit before that. This book, where it came from, was published in 2006. But at present, you can see it's all pitted and corroded and warped in a different way because that limestone has started to dissolve in the rainwater that has run down that statue for years and years and years. And the reason that happens is because limestone is slightly soluble in water. And when I say slightly soluble, I mean slightly soluble, just a very small amount. But if you keep rushing water down through years and years and years, it's going to start to dissolve. I mean, how do you think the Grand Canyon got cut? I mean, some of it's erosion, but some of it is you start to dissolve some of those rocks after millions and millions of years. You can dissolve rock because you're rushing by so much water. So, things that we wouldn't necessarily think are soluble, they actually do dissolve in water, at least to some extent. And, if we look at calcium carbonate, CaCO3, it dissolves to produce calcium ions and carbonate ions. Notice the way that we wrote that expression. When we deal with equilibrium, all right, we have to conform to whatever form of the chemical equation equilibrium is expressed as. And for solubility, it always is 1 mole of whatever compound we're dealing with or we're trying to understand the solubility of it as a solid in equilibrium with calcium ions, the ions that make up that compound, which are calcium ions and carbonate ions. So 1 mole of the compound to dissolve in equilibrium with the ions. Now you have to be careful because you've got to balance out the number of ions. It's nice for calcium carbonate because it's 1 mole of calcium and 1 mole of carbonate. But it doesn't always have to be that way. If it were calcium chloride, CaCl2, it would break up or dissolve to produce 1 calcium ion and 2 chloride ions. Now, the equilibrium constant for this particular type of an expression, remember solids drop out of the equilibrium expression. So if we're going to write this equilibrium constant, it would be equal to the concentration of calcium times the concentration of carbonate, and there's nothing else there. So we call that product of those ions, we call that the solubility product, KSP, equilibrium constant for the solubility product. And for calcium carbonate, that's 3.8 times 10 to the minus 9th. So when you put a rock, a piece of limestone into some water, the product of the calcium ion from the dissolution of calcium carbonate and the carbonate ion from the dissolution of the calcium carbonate, the limestone, as you put it into the water, that product is going to be 3.8 times 10 to the minus 9th, meaning those concentrations are exceedingly small, about 10 to the minus 5th each. So they're going to be really, really tiny. It's not going to dissolve a lot. All right, so if we think about this solubility product constant, all right, there's some value in being able to look at it and trying to determine how soluble something is. So if we look at PbCl2, all right, it has a solubility product constant of 1.7 times 10 to the minus 5th. But if we look at something like PbI2 has a solubility product constant of 8.7 times 10 to the minus 9th, meaning that lead chloride is more soluble than lead iodide. You have to be careful about making these comparisons because Here I'm comparing lead chloride and lead iodide because they're similar in stoichiometry. So one lead ion and two chloride ions, one lead ion and two iodide ions would come from that. So we have to be careful and we have to choose things to compare in a way that they're comparable, because there are some other things where it may not be nearly as simple as doing that. Like I would compare silver bromide with silver chloride to compare and find which one's more soluble. Now the interesting thing about this is, all right, if we think about it, you did some of this whenever you did what do we call qualitative analysis, where you did all the chemical reactions to determine what ions are present. And you remember the one part where you had to take and you had to add some hydrochloric acid to your solution, and that solution contains silver and lead. And to precipitate the lead chloride, you had to cool it. All right, you had to make it cold, so you put it in an ice bath. And that's because the lead chloride isn't, I mean, it's fairly soluble. And so you can get it to dissolve, and in order to get it to not dissolve, you've got to cool it down. And the reason why you do that is because what happens with solubility is it's dependent on temperature. At higher temperature, the KSP will change. At lower temperature, the KSP will change. And generally, the KSP gets smaller as the temperature gets smaller, and the KSP gets bigger as the temperature gets bigger or larger. All right, so that sort of gives us an intro into solubility. We're going to then go and look at the nuts and bolts of how to do a calculation in our next, and do the calculations in our next video.